Thank you for joining us today. Let me acknowledge the traditional custodians of the land that we host the webinar from. It's Wurundjeri Woi people, the Kulin Nation. That's their land that I'm joining. I'm kind of represent when I conduct the webinar and host the event today. So for probably, you've kind of heard about the topic. Earlier we had webinars conducted on different types of topics, which are more towards procurement, education, capability building. And so this is an area which is quite, I would say, evolving and advanced, but at the same time, I've got two speakers today who are able to talk about the advancement of material science in a very simple way. So I would like to welcome Matt and Ale to the webinar, Alessandra. The topic is on forward thinking on material design. So just to give a brief introduction about Anvata. So we are an organization which is functioning primarily with the objective of helping corporates and other organizations to transition to a clean and regenerative model. So there are a couple of things that we do, and capability building is one of the areas we are specializing in. So we are building a small educational hub. There are 9 courses in the pipeline. 3 of them are launched, and there's a knowledge hub under development to kind of share more resources as well. So we help companies with transition into a regenerative model. Some of the work we do fall in management consulting, some in sustainability consulting, studies such as life cycle assessments, material flow assessments, as well as things like developing transition roadmaps. We are also in the early stage of building a tech product, a capability assessment tool, which I think we could share later if you are interested to know more about. So about who's speaking today, I'm actually not speaking today. I'm acting as a moderator. Who's joining with me today are Matt, who's a professor at Deakin University. And he's with 30 years experience specializing in creating and developing advanced alloys and also advanced recycling processes. So he's probably a strong advocate of material design for a circular economy. And Matt's basically was leading the Institute for Frontier Materials for a couple of years. And now he's, where are you joining from, Matt? What's the city you're joining from today?
I'm in France.
France, yes. Is there a particular city? And I hope it's okay to tell them.
I'm in the Périgord region.
Okay, beautiful. And Ale is joining from the Institute of Frontier Materials today. So Ale is also kind of a very, has a broad scope of expertise in terms of material design, specializing in developing new technologies for materials manufacturing, including nanomaterials, and has a focus on making the industry sustainable and also material development for a circular economy. So she's currently working at Deakin part-time and also acting as the Science and Technology Australia's TIM ambassador, providing evidence-based analysis for policy decision-making by the government. So I probably would leave more time for their talk and questions. And let me start with a small preamble about our topic. So coming from a very general perspective on how we talk about a linear economy and a circular economy. So we all know that in a linear economy, we have this paradigm where we purchase, use, and dispose of things. So I typically take this example of a washing machine where if you want to buy wash clothes, what we are thinking of in a linear economy is purchasing the device, which is the washing machine, using it, and disposing or diverting it to recycling at the end. In a circular economy, we start at a higher level. So we kind of question the broad purpose of why we need things. We start with the fundamental human need, which is, in this case, washing of clothes. And there's the service or the utility that is associated with it is washing clothes. and washing machine is the product that we need for that. And every product is made of components, and those components are made of materials. So if you see the watch on the right hand side, watch is the product. All the metal strap, the frame of the clock, and all the other small parts in it are components, and each of them are made of different types of materials. And from another kind of a very general perspective, when we talk about different alternatives towards a circular economy, we are trying to optimize the extent of regeneration, how we are able to reuse, refurbish, remanufacture, or maintain these components and materials. We are increasingly trying to dematerialize, which means reduce the dependency on extracted material, have more services to service the materials, and have the quantity of material flowing in the economy to be low. We are trying to enhance the performance of asset, and at the same time dealing with the objectives of decarbonization, which means we don't want to add the activities which are non-value adding, which would increase the carbon emissions or the greenhouse gas emissions associated. So increasingly, or all the time, we are juggling with these 4 concepts: regenerating what we have, dematerializing, increasing the performance, and reducing the impact. So when we are trying to do that, all the time, we are living in a world of material. So what we try to address through LA's talk and Matt's talk today are this type of questions. What do we aim to achieve through a circular economy or a regenerative economy through the design of materials? What does proactive upstream material design for a circular economy look like? What strategies and design and development concepts are currently being used? So what we have as a lineup today, I gave the brief preamble, and Matt and LA, who are, I think, world-class researchers in this area, they talk about, Matt would talk about the circular economy, a perspective from a material science institute, and LA on more practical examples and case studies on material design for a circular economy. And at the end, we would have some time for Q&A. So I'll hand over to Matt. Sorry. I'll stop sharing.
Thank you. Yes, thank you, Mayuri. I'll share my screen, and good afternoon, everyone. Give me 1 second. I might just ask for a confirmation in a second that you have.
Yes, we can see your screen.
It's still good?
Yes.
I might just, you've seen me, I'll say hello. I might turn my camera off because I'm on battery power in a remote location. So hello, everyone, with my face. Now to remove my face. Okay, so as Mayuri said, I work for a materials research institute, the same as Ali, and we're passionate about the circular economy. And so I'm going to spend a few minutes now largely probably just trying to define a circular economy from how we look at it from a materials perspective. So here is a view that is commonly employed, and Mayuri kind of already covered this. I like to think of the circular economy as trying to head from left to right on this plot. But this is just very conceptual, and it's worth, as Mayuri already said, trying to drill down the definition a bit tighter to see how we can actually implement these concepts from a materials perspective. And so one common definition is given here, where circular economy aims to keep products, components, and materials at their highest utility and value at all times. And from a materials person, that means a number of things, and I'm going to take you through how we translate that to materials thinking. But I'd like to present to you a slightly different way of thinking about this same issue as follows. So a slightly different view is that a circular economy, amongst all the other things you've already heard from Mayuri, aims to lower the energy cost of convenience. It aims to lower the energy cost of convenience. So let's try and work through that, the energy cost of convenience. So what is convenience? In this definition, it's the continued availability of materials, components, and products. So to have them continually at hand requires energy. So because things wear out, obviously, they break, and then of course we want new ones. So the continued availability requires repair and replacement, as well as manufacture. And that these all cost energy, because energy requires emissions as well. I think this is quite a useful way to think about the challenge, and it certainly helps our thinking in the material space of how can we lower the energy cost that is associated with convenience. So let's just work through this a little bit. Mayuri's already given the nice washing machine example. So here's a cousin to that. This is a toaster example. So, of course, to produce a toaster costs energy to manufacture. Energy to manufacture all the different materials, to extract them, and to combine them and to produce the toaster. And then, of course, we use the toaster. Yes, it uses energy to provide the service, but that's not something as a materials person we're focusing on here. We're just simply focusing on the energy required to supply the convenience of being able to toast. And so during use, in some cases, there's energy to repair. And then its life will end, as it does in our house, reasonably frequently. Then there's the energy needed to manufacture a new one, and so on. This is a continual cycle for a product such as a toaster. And so the question as a materials person we can ask ourselves is, how can we lower the energy cost of this process of continually supplying us with the convenience of being able to toast? And so I'm going to present you, it's going to come across a little bit like a lecture, so I hope it's not too lectury for you, but a framework of looking at this. And so get ready for it. It's a bit of a graph coming up now. Okay, so let's work through this. So don't freak out. Just go with me. So what are we doing here? We're considering the energy cost in providing one of those life cycles. And then we're considering also how long the cycle lasts. These are the things that we have to play with, and the energy cost over time of the ongoing convenience that we're provided with. So the graph here, it's confusing at first sight, but if we work through it, it's quite simple. The bottom axis is just time, just the time that progresses, and then we're having a snapshot of one product life cycle. And then on the vertical axis, we are plotting the energy that are consumed to supply that convenience. And of course, associated with energy consumption as carbon dioxide emissions. And so what we see here is, if we just follow the bold lines here, at some point in time, we have a product or a material, and then we get to a point in its life where it needs some repair, and repair costs energy as well. So however you're fixing it, it's an energy cost, and then you get a bit more life, and then eventually we need a new one, and there's an energy required to replace it, either to produce a new one or to refurbish. And then what that does, though, that provides us with a slope here, which can give us the energy cost of continued availability. It's the slope of this line. And so as a materials person, and we want to analyze how we can contribute to lowering that energy cost of availability. And now I'm just going to simply walk you through a couple of ways that we do it using this little graph as a framework.